Time does not tick. He does not move. He does not care. But people do. People care a lot about time. They wake by it, sleep by it, race against it, obey it. And for most of human history, no one could measure it precisely. The first clocks were shadows. Sundials, stones and sticks placed carefully in dirt or marble. As the earth turned, the sun moved and shadows shifted, stretching across carved lines to mark hours. But sundials do not work at night, or when the sky is cloudy, or in winter. But others invented water clocks, also called clepsydras. These devices let water drip slowly from one container to another, measuring time by the rising level. Some were simple bowls, others were more elaborate with valves and gears. But water flows unevenly with temperature. These clocks were not precise. In ancient China, candle clocks burned at steady rates. Knots tied in the wax-marked intervals. As the candle burned, each night would fall, sometimes triggering a bell or small weight. These were timekeepers for dark places and quiet monks. But still not accurate, but better than guessing. By the 14th century, Europe began building mechanical clocks. Use escapements, pendulums. Heavy weights would fall slowly, turning wheels and striking bells. These were large, public, often in cathedrals. Time became not just a feeling but a schedule. Villagers heard the order. People began to wake on time or be late. Clocks got smaller. By the 17th century, pendulum clocks became the standard. Invented by Christian Huygens, based on Galileo's ideas. They used the swing of a pendulum to regulate motion, the steady arc ticking back and forth. These clocks lost only a few minutes per day, a major achievement. Then came marine chronometers. These were crucial. Sailors needed to know longitude, their east-west position on Earth, to navigate from back. But longitude requires knowing time, and the ocean is not kind to pendulums. So in the 18th century, John Harrison, a self-taught English carpenter, created a clock that worked at sea. No pendulum, it used springs and counterweights. His clock, H4, changed navigation forever. Ships stopped getting lost. Not all of them, but many fewer. In 1840, clocks got connected. Railroads needed precise time. Trains ran on tight schedules across long distances. Before that, each city used local solar time. Noon was when the sun was highest. But in England, that meant Bristol time was 11 minutes behind London time, a recipe for disaster. So the world began to synchronize. Telegraphs sent time signals. Stations set clocks together. Time zones were born. Then came quartz. In 1927, Bell Labs created the first quartz clock. It used the regular vibrations of a quartz crystal under electricity. No gears, no pendulums, only precision. These clocks lost just seconds per year. Today, almost every digital watch, phone, and oven uses a quartz crystal to keep time. It is invisible, but always ticking. Yet even quartz is not perfect. The most accurate timekeeping on Earth comes from atomic clocks. Invented in the 1050s, they use the vibrations of atoms, usually cesium-133, to measure time. These vibrations are consistent. Exactly 9,192,631,770 vibrations per second. That number, not an estimate but a standard, defines 1 second. Not the swing of a pendulum, not the drip of water, but the quantum tick of an atom. Atomic clocks are so precise they would lose 1 second every 100 million years. They are used in satellites, GPS systems, global data centers. Without them, positioning systems would drift, bank transactions would desynchronize, scientific experiments would be flawed. And still, even the best clocks do not define time. They only measure it, and even that measurement is a construct. The idea of now is not universal. Due to relativity, time moves differently depending on gravity and speed. A clock on a mountain ticks faster than one at sea level. A clock in a plane ticks differently than one on the ground. Time is not fixed, but it can be measured. And for now, that is enough. There are 86,400 seconds in a day, 60 in a minute, 60 in an hour, 24 in a day. But these numbers are not absolute. Earth does not rotate evenly. It slows slightly each year, but every few years the world adds a leap second. Our next trick, just to keep time aligned. Calendar is also imperfect. The year is not exactly 365 days. It's 3652422. Every 4 years we had a leap day, February 29th, except not every 4. Years divisible by 100 don't get a leap day, unless they're also divisible by 400. It is complicated, because time is complicated. Humans made clocks to measure something they cannot see, to organize something they do not control. Who devised something that keeps moving? Seconds are not physical objects. They are decisions based on movement. We're planets of atoms, of thoughts. In the end, time remains steady and unknowable. It moves slowly when we are bored, quickery when we are late. Strength stretches in memory. It falls in grief. It vanishes in sleep. Some philosophers say time is an illusion. Others call it the only real thing. Physicists define it as a dimension. Psychologists call it perception. But clocks do not ask questions. They just will vibrate, or glow, a digital display in the night, a ticking wall above the kitchen door, a sunrise that arrives when it should. Mostly, the burst clocks use shadows. The newest ones use atoms. And both are trying to answer the same question. What time is it? And silently, how long do we have? Dust is not just dirt. It is not just what settles on forgotten bookshelves or what dances in slanted sunlight near windows. Dust is far more complex and far more common than most notice. It is everywhere. In homes, in air, in deserts, in galaxies. Dust is ordinary, but its story is surprisingly long. The word dust comes from Old English dust, meaning fine particles or ashes. It has no specific shape, a fixed size. But generally, dust refers to particles less than 500 micrometers in diameter, about 5 times the width of a human hair. It's small enough to float, but not quite invisible. Household dust is not one thing. It is many things. Dead skin cells, textile fibers, dried soil, pollen, insect parts, bits of plastic, even space dust. About 80% of the dust in the average home is carried in from outside. Shoes track in soil. Open windows invite pollen and ash. Air vents spread particles between rooms. The other 20% is generated indoors. Shed skin, mostly. Humans lose 30,000 to 40,000 skin cells every minute. Not all of it becomes dust, but much of it does. Dust mites eat skin flakes. They are microscopic, typically 0.2 to 0.3 millimeters long. They do not bite. They do not live on humans. But they live near us. In pillows, mattresses, carpets, curtains. The warm, humid bed is ideal. A typical mattress may contain between 100,000 and 10 million dust mites. They excrete. Their waste dries. It becomes dust. This is called mite fecal matter. And it is everywhere. It floats in sunbeams. It settles slowly. Dust can carry smells. It can carry chemicals. It can carry memories. In old libraries, the smell of must comes partly from paper dust. As books age, they break down into lignin-based particles. It is drift. These accumulate. In attics, dust gathers in corners. On lampshades, in time, there is industry. In factories and mines, fine particulate matter can be hazardous, known as PM10 or PM2.5. These are particles smaller than 10 or 2.5 micrometers, but they can enter the lungs, stay there, cause disease. Coal dust, metal dust, silica, asbestos. In certain industries, dust is monitored carefully, suppressed with sprays, filtered with masks. It can ignite. in sawmills, grain silos, or sugar refineries. Airborne dust can cause dust explosions. There is desert dust. In the Sahara, dry winds lift sand and dust particles high into the sky. Each year, 180 million tons of Saharan dust cross the Atlantic Ocean. It reaches South America, the Caribbean, even Florida. It fertilizes the Amazon rainforest. The minerals in this African dust help plants grow in soil that would otherwise be depleted. Dust travels farther than people expect. It hitches rides on wind, on pressure systems, on storms. There is volcanic dust. When a volcano erupts, it sends ash, a fine, sharp dust of pulverized rock and glass into the stratosphere. This dust can stay suspended for years. It reflects sunlight. It cools the earth. After Mount Tambora erupted in 1815, global temperatures dropped. 1916 became known as the year without a summer. Dust can change climate. There is cosmic dust. Space is not empty. Between planets, between stars, between galaxies, there is dust. Tiny fragments of carbon, iron, silicon, leftovers from the birth and death of stars. Microscopic grains, 1 to 100 micrometers wide, drifting through void. Earth encounters thousands of tons of cosmic dust every year. So much of it burns in the atmosphere. Some settles quietly on rooftops, in ice sheets, in oceans. Most people have unknowingly touched space dust. Lunar dust is different. During the Apollo missions, astronauts found that moon dust stuck to everything. It was jagged. It was electrostatic. The moon has no atmosphere, no weather, no erosion. Its dust is sharp like glass. Its scratched helmets, irritated lungs, torque through seals. Dust on the moon was not soft. It was ancient and dangerous. There is pollen dust. The trees release grains in spring, grasses in summer, the ragweed in autumn. Pollen dust travels in puffs. It settles in those. It triggers sneezes. Where all dust is dead. Some of it is plant intention, attempt to reproduce, carried on wind. There is dust in comets. Dust in Mars storms. Dust in computer fans. Dust in history. In 1934, a massive dust storm blew through the Great Plains. Drought and poor farming practices created the Dust Bowl, a period of severe ecological collapse. Black clouds of soil blotted out the sky. They reached as far as New York. Farmers abandoned their land. It was dust, not war, that reshaped a region. Dust can be carbon, or chalk, or powdered skin. It can be dangerous, or poetic, or invisible. To clean dust is to move it, to wet it, to vacuum it, to contain it. But it comes back. It's always coming back. In the air, on the body, on the world. A room left empty will still gather dust. A room filled with life will gather more. It is a record of activity, of silence, of skin, of decay. In physics, dust is sometimes used in models to describe galaxies. A dust approximation means treating stars as simple particles. A dust cloud is not always dusty. It can be mathematical. In religion, dust is symbolic. Dust to dust. Ashes. Ends. Beginnings. In poetry, it is a metaphor. In science, a substance. In clean, an enemy. Yet dust is not aggressive. It does not arrive with force. It weighs. It falls. It settles. It does not speak, but it is always present. Dust is patience made visible, entropy made soft, silence made physical. Every time light passes through a dusty room, it reminds us that particles are not gone. They are drifting. They are gathering. They are simply in the air. Just there. Ink is older than paper. Before writing, there were markings. On stone, on clay, on bone. Charcoal, ash, blood. Anything that left a trace. But real ink, liquids flowing, intentional, came later. a mixture of water, pigment, and binding agents. The oldest inks were not black, they were red, iron oxide or ochre mixed with water and plant gum. They clung to cave walls in patterns and prints, painted hands, animals with too many legs, spirals without reason. Later, Egyptians used carbon black, a byproduct of fire, collected soot, mixed it with water and honey, sometimes oil, sometimes gum arabic, a thick, dark liquid, pressed into reeds and applied to papyrus. Ink is not paint. It is thinner, more obedient to paper. It wants to flow, to be absorbed, sustained, not sit. By the 4th century BCE, China had developed ink sticks, hardened blocks of soot and glue. These were ground on flat stones with water to make ink on demand. They were used with brushes, fine, controlled, elegant. Calligraphy was not just writing, it was art, and ink was the medium. In Europe, by the Middle Ages, ink turned acidic. Iron gall ink became standard, made from crushed oak galls, plant tumors caused by wasps. These were boiled with iron sulfate and water. The result was bluish black, permanent, sharp, a bit into parchment. It oxidized. It grew darker with time. Many medieval manuscripts, personal letters, and early scientific records were written with iron gall ink. Leonardo da Vinci, Isaac Newton, Beatrix Potter. But it was corrosive. Over centuries, it ate through the very pages it preserved. Printing ink arrived with the printing press. Johannes Gutenberg in the 15th century needed something thicker than traditional inks. His metal typefaces crushed liquid inks. So he created oil-based ink. Viscous, sticky, made from soot, linseed oil, and varnish. It dried slowly, but it stayed in place. It transferred well from raised type to paper, and it made books reproducible. Ink became mechanical. There are different kinds of ink. Pigment-based inks use solid particles suspended in liquid. These sit on the surface of paper, resist fading, used in permanent markers, fine art pens, archival printers. Dye-based inks dissolve completely. They soak into paper fibers, vibrant but less stable, used in fountain pens and many consumer printers. Gel inks are thicker, and smooth, popular in modern pens. They combine dyes and pigments in a water-based gel. They write on glossy paper. They dry quickly. People like how they feel. Ink dries in stages. First, evaporation. Solvents like water or alcohol evaporate into air. Second, absorption. Remaining dye or pigment embeds into the paper. Third, oxidation or polymerization. Some inks react with oxygen. Others form long chains of molecules. The process can take seconds, or hours, or days, depending on humidity, temperature, ink composition, and the nature of the surface. Ballpoint pens use oil-based ink. It is thick. It does not leak. The tip contains a tiny ball, usually made of steel or brass, which rotates as the pen moves. It draws ink from the reservoir to the page. Friction controls flow. Invented in the 1930s by Laszlo Bira, a Hungarian-Argentinian journalist, tired of smudging fountain pens, who watched printing presses, noted how quickly their ink dried. He adapted the idea into a pen. Today, billions are sold every year. Fountain pens use capillary action. Ink flows from a reservoir through a narrow feed, drawn by surface tension and pressure. No push, just passive flow. Fountain pen ink must be thin. Cannot clog, not dry too fast. It is sensitive. Fountain pens bleed on cheap paper. Es friend, they fito. But on good paper, they glide. They write in silence. Ink is not just black. There is sepia made from cuttlefish. Indigo, extracted from plants. Ultramarine, once made from crushed lapis lazuli, more valuable than gold. Volatile iron, complex and reactive. Modern inks come in infinite colors. mixed with care. Sometimes synthetic, sometimes organic, some shimmer, some shift. Some vanish under UV light. Invisible ink exists. Lemon juice? No. Cobalt chloride? When heated, these inks darken. Messages appear. Used in espionage. Used in games. Used in childhood. It is not permanent, but it is secret. Tatooine is different. It is injected into skin, into the dermis, the layer below the epidermis, too deep to flake off, too shallow to bleed away, made of pigments suspended in carrier fluids, sterile, regulated, sometimes metallic, sometimes plant-based. The body treats it as foreign. Immune cells surround the pigment, but cannot remove it. The ink stays, mostly. Printer ink is a commodity, sold in cartridges, measured in drops, often more expensive than blood. Most home printers use CMYK, cyan, magenta, yellow, and black. By layering dots of these four colors, almost any shade can be created. It is slow, precise, temporary. The ink fades unless treated, unless archived. Ink has no consciousness, but it carries meaning. It records ideas, romance, diagrams, matters, mistakes. Ink can stain. Ink can preserve. Ink can be erased or not. In ancient contracts, ink meant commitment. Signatures in ink were sacred. To break a written agreement was not just a legal offense, it was a betrayal of ink. Even today, wet ink signatures remain important, despite digital forms, despite typed names. There is something final about ink. It is intentional. Ink appears in nature. Cuttlefish and squid eject ink clouds when threatened. Dark, viscous plumes, used for camouflage, distraction, escape. Cephalopodin contains melanin, like human skin. It is ancient, protective. When a pen runs dry, it does not break. It simply fades. When ink fades, it does not disappear. It waits. It stains. It becomes part of the surface. Some inks resist time. Others surrender. Ink and paper were never required. Ideas could live in memory, in style, or voice, but ink made them mobile, portable, and shareable. Ink allowed replication and repetition and permanence. Today, most ink is digital, simulated pixels, not liquid, but people still write, still scribble, still underline. Ink has not vanished. It has adapted. A single droplet of ink on paper can hold meaning for centuries, or be forgotten immediately. It depends on context, on content, on care, but the ink remains. Quiet, stable, present. It does not ask to be seen. It only marks, softly, permanently, until it does.